Modern physics lacks a unified ledger for energy conservation. Under current models, measurable energy can be subtracted from the universe without being assigned to a recipient. This occurs because of the redshift boost parity anomaly. When a massive object accelerates, undergoing a Lorentz boost, we observe direct physical consequences. The object compresses along its axis of motion, and its internal clock slows down. However, the rules shift when this exact same mathematical transformation is applied to a photon. For a massive body, these transformations are treated as real mechanical stress and time dilation. Yet when a photon undergoes an identical boost and experiences a redshift, those physical sequelae are ignored. Standard applications classify this change in the photon's frequency as a kinematic artifact, a coordinate effect, rather than a physical interaction. But frequency is a direct measure of a photon's energy. To measure a redshift is to record a reduction in its physical energy. Assigning physical reality to matter transformations while dismissing them for light creates a category asymmetry. If the photon loses energy without a receiver, the accounting ledger for the universe no longer balances. This bookkeeping failure is built into the standard vacuum idealization. In general relativity, modeling empty space involves setting the stress-energy tensor to 0. This leaves the simplified vacuum assumption, the Ricci tensor equals 0. This assumes spacetime is a passive manifold that only curves when mass is explicitly inserted. Without matter, the math suggests the vacuum is perfectly flat and inert. The spacetime occupancy framework rejects this assumption as a mathematical shortcut that does not exist in the physical world. If a photon loses energy while traveling through an idealized empty vacuum, there is no reservoir to receive it. The energy simply vanishes. To maintain this model, cosmologists often admit that global energy is not conserved in general relativity. It is a choice to abandon a foundational conservation principle to keep the vacuum idealization intact. The STO framework provides the correction by redefining symmetry and conservation as a recursive ledger. By treating the vacuum as an active participant rather than a passive background, we can track energy as it moves between radiation and spacetime curvature. The physical vacuum is universally occupied. Every region of space is threaded by a persistent radiation background, from the Big Bang to starlight. Because this photon flux never vanishes, the stress-energy tensor is never truly 0 anywhere in the cosmos. We can prove this by contracting the Einstein field equations with a null vector, the mathematical path of a light beam. If we substitute the properties for radiation, where pressure is 1/3 of the energy density, the result is strictly positive. This confirms that along any real light path, the spacetime region cannot be Ricci flat. Electromagnetic amplitude and intensity function as a direct source of spacetime curvature. This integrated curvature from the radiation baseline provides a non-zero convergence. It is a source of gravity that standard models frequently misattribute to dark matter. Redshift is not an energy loss, but a measurable transfer. The energy moves from the photon's phase directly into this omnipresent curvature ledger. Conservation laws are defined by continuous symmetries. This is the foundation established by Emmy Noether. Standard physics uses the Poincare group, which treats uniform rotation as a purely spatial phenomenon. This ignores the temporal structure of rotation. Constant angular velocity requires temporal phase locking. Every part of the system must complete a revolution in the same time interval. Discarding this spatio-temporal coupling is the specific error that erases the energy ledger in rotating systems. The STO framework identifies a missing invariant, the helical killing vector, which couples time translation and spatial rotation. From this symmetry, we derive a specific Noether current. This resolves into the helical charge, Q omega. It is the true conserved invariant for any phase-locked rotating system. In these systems, energy and angular momentum are not conserved separately. Only their combined helical charge remains constant. This restores parity. Both the inertial stress in matter and the frequency shift in light are manifestations of the same helical invariance, booked correctly in the STO ledger. Treating the vacuum as an active curvature ledger forces a specific look at the equivalence principle. There is a disconnect in our current understanding. Objects in gravitational freefall experience no resistance, yet accelerating that same mass through a vacuum yields resistance proportional to its mass. Why does mass resist motion in an empty vacuum, but yield completely in a gravitational field? The STO framework suggests mass and inertia are emergent properties rather than intrinsic attributes of matter. Under this model, mass measures resistance to displacement from a natural geodesic. It is an angular memory of where a particle belongs in curved time. In freefall, the reference frame intersects the object's geodesic harmonically. There is no displacement, so there is no resistance. In a vacuum, forcing a mass off its geodesic creates informational resistance against the background curvature field. The equivalence principle emerges here as a geometric outcome. Inertial and gravitational mass are reconciled as two ways of measuring the same temporal curvature. This framework is a predictive theory. Its value depends on its ability to be experimentally falsified. One primary test uses a whispering gallery resonator. We can monitor the frequency drift of a face-locked microtoroid as it rotates. After subtracting Sagnac and thermal effects, any residual frequency drift must scale exactly to the helical charge constraint. A second test looks for cosmological radiation baseline focusing. If we correlate maps of the extragalactic background light with weak lensing data, we should find a positive convergence baseline of approximately 10 to the negative 3. A positive detection would empirically link electromagnetic amplitude to localized space-time curvature. If these residuals vanish when the phase lock is broken, the STO ledger hypothesis is falsified. By including time in our symmetries and treating the vacuum as a physical ledger, we restore global conservation. The universe does not leak energy over time, it simply stores it directly in the geometry of